video we will discuss some more problem based on one-dimensional wave equation. Here we have one problem stated as a tightly flexible string has its ends at x is equals to 0 and x is equals to L. At time t is equals to 0, the string is given a shape defined by fx is equals to lambda x L minus x, where lambda is a constant, and then released, that is del u upon del t at time t is equals to 0 will be 0. It means initially it is in a fixed position, fx is equals to lambda x into L minus x. It's independent from t, that's why del u upon del t at t is equals to, initially del u upon del t will be 0. Also it's given that its tightly flexible string has its end point x is equals to 0 and at x is equals to L. So at x is equals to 0 and at x is equals to L, u will be 0. Now we are to find the displacement of any point x of the string at any time t greater than 0. Now to solve this problem, first we assume the general equation of a string is one-dimensional wave equation. So it will be del 2u upon del t square is equals to c square del 2u upon del x square, or del 2u upon del x square is equals to 1 upon c square del 2u upon del t square. Now we write which are its boundary condition and what about its initial condition. Its boundary condition means based on position is u0t is equals to 0. It means at any time t at position x is equals to 0, u0t will be 0, and at any time t ult, L is end point, another end point, ult is also 0 from the first line of problem. And now the initial condition, as it says, at the time t is equals to 0, the string is given in a shape defined as fx is equals to lambda x L minus x. It means at t is equals to 0, u will be lambda x L minus x. So at x and t is equals to 0, ux0 is equals to lambda x into L minus x. And at that time t is equals to 0, del u upon del t will be 0. When we differentiate it partially, we get 0. So at t is equals to 0 means initially the partial derivative of u with respect to t is 0. Now taking we assume its solution using separation of variable method, ux is equals to x into t. Now we will differentiate it twice with respect to x and t partially, and putting those value of derivatives in given equation, we get in assume the wave equation, which is del 2u upon del x square is equals to 1 upon c square del 2u upon del t square. We get 1 upon x d2x upon dx square is equals to 1 upon c square t d2t upon dt square is equals to lambda. Here lambda is some assumed constant. Now here we take lambda is equals to minus n square. Lambda is constant which can assume any value 0, positive, as we have discussed in previous lecture, lambda cannot take a positive value or 0, because in that case the solution does not contain any no term of sine and cosine, which must contain in a wave equation. That's why we reject the possible value of lambda like 0 and positive value of lambda. Here we take only negative value of lambda. So let's take lambda is equals to minus n square. So using first and the third fraction, we get d2x upon dx square plus n square x. When lambda is equals to minus n square, it gives us d2x upon dx square is equals to minus lambda x square, lambda x, and when lambda is minus n square, and when we shift it into left hand part, it gives us d2x upon dx square plus n square x is equals to 0. Similarly, from second and third fraction, we get d2t upon dt square plus n square c square t is equals to 0. Now we will solve these equations, as these both equations are ordinary linear differential equation with constant coefficient, and as the right hand part is 0, so only complementary function is their solution. So in first equation, its auxiliary equation is m square plus n square equals to 0. It means m is equals to plus minus iota n, and in that case solution can be written as x is equals to a cos nx plus a2 sin nx. Similarly, for second equation, solution can be written as t is equals to b1 cos nct plus b2 sin nct. Here small t is independent variable and capital T is dependent. Capital X is dependent variable, small x is independent variable. Now we'll put these value x and t in assumed solution, which is here, as we assume u is equals to x into t. So we'll put this value in this equation 2. We get uxt is equals to a1 cos nx plus a2 sin nx into b1 cos nct plus b2 sin nct. Now we will find the values of these arbitrary constant a1, a2, b1 and b2. So first we use boundary condition, which are at x is equals to 0, u0 t is equals to 0, and at x is equals to l, u l t is also 0. So first we put x is equals to 0 in equation number 3. We get 0 is equals to a1 cos 0 is 1, so we have a1 plus a2 sin 0 is 0, so here we get 0, and this is independent of x. So b1 cos nct plus b2 sin nct is a non-negative term. So when we solve it, as its left hand part is 0, from here we get a1 is equals to 0. Now we will put x is equals to l, ult, it's 0 using boundary condition, is equals to a1 cos nl plus a2 sin nl, and this is a non-zero term. As we have already found the value of a1, which is 0, so from here we get a2 sin nl is equals to 0. Because a2 can't be 0, that's why sin nl must equals to 0. So nl is equals to m pi. For all integer natural values of m pi, sin m pi will be 0. So nl is equals to m pi. From here we have the value of n is equals to m pi upon l, where m belongs to capital M are natural numbers. So we will put these value a1 and a1 and n in equation number 3. The equation 3 becomes uxt is equals to b1 cos, at in place of n we will write m pi upon l, so it becomes b1 cos m pi l ct plus b2 sin m pi c upon l t into a2 sin m pi x upon l. a1 is already 0. Now a2, b1 and b2 are arbitrary constant, so it can be written as summation a cos m pi c upon l. Here a is what? a2 into b1, and b is a2 into b2. Multiplies a2 with b1, we write it as a, and b represents b2 into a2. Now here m belongs to capital N. For distinct values of m we have different solutions, so we write this solution as in summation form. Summation m vary from 1 to infinity. For m vary from 1 to infinity, it can be written as summation m vary from 1 to infinity a cos m pi c upon lt plus b sin m pi c upon lt into sin m pi x upon l. So it becomes in this way, equation 4. Now to find the value of a, m and bm, here we use initial condition. First we use the initial condition ux is equals to 0, u at x and 0 equals to lambda x L minus x. It means at t is equals to 0, solution will be lambda x L minus x. So we will put this value here. Equation 4 becomes lambda x L minus x is equals to summation m vary from 1 to infinity am. Here we will put t is equals to 0, so cos it becomes am sin m pi x upon L. It becomes 1. When we put here t is equals to 0, so it becomes cos 0 is 1. Second term is bm sin m pi ct. When we put t is equals to 0, it becomes 0. So second term will vanish. So here we have only am. So we have am into sin m pi x upon L, for x lie between 0 and L. This is nothing but a half range Fourier sine series. This is half range Fourier sine series for the function fx is equals to lambda x L minus x. So we can find the value of am by using the formula am is equals to 2 by L 0 to L fx sin m pi x by L dx, where fx is lambda x L minus x. Now we can separate this term. So first term is taking 2 lambda upon L outside, we have Lx sin m pi x upon L dx, and second term is x square sin m pi x upon L dx. Now using by parts rule, we will integrate both term, and by integrating this term we get 2 lambda upon L minus 2L upon m pi into L square upon m square pi square cos m pi minus L square upon m square pi square. Now taking minus 2L upon m pi outside, it becomes 2 lambda upon L square upon m cube pi cube. From here we take L outside, this L cancel out, and from these L square taking outside, so in numerator we have L square. So it becomes minus 4 lambda L square, and in denominator we have taken outside m cube pi cube. So we have in denominator m cube pi cube, and inside parenthesis we have cos m pi minus 1, and we, as we know, cos m pi is what? Minus 1 raised to power m. This is 1. So am is equals to 8 lambda L square upon m cube pi cube, where m is an odd number. So this is m, this is m, not z, not m, sorry. This is m. Again, when n is even, it becomes 0. When n is odd, m is 8 lambda L cube upon m cube pi cube, and when m is even, it becomes 0. So it can be written as del u upon del, sorry. So we have calculated the value of am. Now we are to find the value of bm, another arbitrary constant. Now we have to find the value of this bm. Now here we use another initial condition, which is del u upon del t is equals to 0 at t is equals to 0. When we apply this, so first we calculate del u upon del t, which is equals to summation m is equals to 1 to infinity minus m sin m pi ct upon L. We are to differentiate the above equation number 4. We get this term. Now here we put at t is equals to 0, del u upon del t become 0. So it gives us bm is equals to 0. Now in equation 4 we put am and bm, we get uxt is equals to summation m vary from 1 to infinity 8 lambda L square upon m cube pi cube cos m pi ct upon L into sin m pi x upon L. Here m is odd number only. M is equals to 1, 3, 5, 7 and so on infinity. No even term it takes. So that's all about how to solve one-dimensional wave equation. Thank you.